Hello there. In this lesson, we're going to explore collision theory, which is how we explain the differences in reaction rate when you change various factors. Of course, this is everybody's favorite, the elephant toothpaste that I did in class one day. I wasn't quite fast enough to get my hand out of there, but it went off pretty good. Okay, so let's start. So what are some of the things that affect how fast a reaction will go? Well, here we have a list with a few examples. First off is what type of reactants do you have? Even when the reactions are very similar, the differences between the substances can cause reactions to proceed at different rates. So an example here is some sodium in water. You can see it's burning. There's a little bit of flame there. Versus potassium water, which is like this vigorous popping, snapping, clearly faster reaction going on. Secondly is the concentration of the particles. The more that you pack them together, the faster the reaction tends to go. And you can see that as well with the elephant toothpaste there. If I used a lower concentration of peroxide, it doesn't go nearly as fast. Temperature. Temperature, if you increase the temperature, you generally get a faster reaction. One you can try at home is take two glow sticks, stick one of them in ice and the other one in hot water, and you can compare the glow that you get from both of them. And obviously the hotter one should be a lot brighter. Next one here is a catalyst. So there are all sorts of substances that can help reactions go faster, and we'll look at a few of those as we go along here. And finally, the surface area of your reactants. So obviously, I'll use this little Alka-Seltzer tablet here. This is going to react with water, and so the water is going to react wherever there's a surface it can touch. And the more you break it down, the more surface there will be, and you'll be able to get at more of that Alka-Seltzer. And so you would expect this one that's busted into a few small pieces to react faster than the one that's one big tablet. And of course, if you take it down to powder, you've got extreme amount of surface area there, and that should react all at once. All right, so let's have a look at some of how we explain these factors using collision theory. So what is this collision theory, and how can it help us explain all those different factors that affect reaction rate? Well, it has to do with particles that make up reactions. And so here we have this nice graphic where you have particle A reacting with particle B, C. And so collision theory would explain the reaction rate based on how often and how hard those particles collide with each other. And so inside this chamber here, you've got these particles, bouncing around. And a reaction's only going to happen when particles strike each other, like meet at a particular orientation. So this particle has to meet this particle. They have to hit each other with the right amount of energy, and they have to hit each other in the right orientation with respect to each other so that a reaction can occur, so that bonds can be broken and new bonds formed. As far as the particle motion goes, you'll recall that particles don't all move with the same amount of energy in any given sample. In a cooler sample here, you've got a lot of particles here that are moving slowly. And in a warmer sample, you've got a lot more over here that are moving fast, right? So this higher temperature, being greater than the initial one, will have a lot more particles that are moving more quickly, and therefore we would expect more particles to be able to collide and be able to have effective collisions. So the energy component of collision theory is that when two particles meet, there has to be sufficient amount of energy to get the reaction to occur. And that amount of energy is called activation energy. Activation energy is used to break bonds that exist in the reactants. And of course, there's every particle is going to be surrounded by a bunch of electrons that repel each other. And so there has to be a minimum amount of energy to overcome that repulsion as well. And so once that minimum amount of energy has been released, well, then the reaction can occur, and then even more energy can be released if it's an exothermic reaction, and that'll be the extra energy that's given off. So that difference between that initial state and the activated state is the activation energy, E act, and that's going to govern how part of how quickly a reaction will go. Now, if you remember that all those particles inside a reaction are not all moving with the same speed. When you change or look at different amounts of activation energy, there's going to be different number of particles that are going to have that amount. So if this curve here represents all the particles in a sample, and sample A reacts at a lower, with a lower amount of activation energy, that means that all of these particles, all the particles under the line here, those would all react. And then if you have another reaction, reaction B here, reactant B, if it requires more energy in order to react, it has a bigger activation energy required to get the reaction. That means fewer particles are going to have that minimum amount of energy, and therefore it's going to be slower because fewer particles are going to be able to attain that. So how do we explain the differences between reactions based on the characteristics of the compounds? Well, of course, different compounds are going to have electrons at different distances. They're going to have bonds with different strengths. And of course, there's that orientation piece also that plays a part. If it's harder, or if there's fewer orientations that will work for the reaction to proceed, then you're not going to get as rapid a reaction. So if we have this example here where we have like molecule A reacting with molecule B, and they only really react if they hit each other on the side like this, if it's the sides that collide to make this activated complex. If that's the only way in which the reaction can occur, then there's only going to be a certain odds of the particles hitting each other that way, and therefore a certain speed or rate in which the products are going to form. Anything other than that, and you'll get what you call like an ineffective collision. And those particles will just bounce off of each other and have to wait until they hit another particle with the right orientation. So the chemical nature plays a part due to the restrictions there might be on what an effective collision is. Now, concentration, most people can figure it pretty intuitively. If particles require collisions in order to react, if they're spread out, then a collision becomes less likely. So at high concentration, you've got a lot higher odds of particles meeting each other, and therefore you're going to get a higher rate of reaction. And then at low concentration, of course, you're going to have the lower chance or lower rate of reaction. So usually that one's pretty easy to figure out. It works for pressure too. If you increase the pressure by forcing the particles closer to each other, that will cause the reaction to go faster as well. Surface area is another factor affecting reaction rate, which is usually pretty intuitive once you have the idea of collisions being how reactions proceed. So if you have a chunk here of a reactant and it's going to have to react with other particles, then the particles can only interact with the parts that are exposed. The internal parts of this chunk of reactant aren't going to be able to react to give you any more product. And then if you bust it up, if you take this same cube and make 8 small little cubes out of it, well then you got a lot more access for the particles to hit each other on a lot more surfaces. And so greater surface area generally means faster reaction. So temperature is another one that's fairly intuitive when it comes to collision theory. Most people understand that if you heat up your pot, that your pasta will boil a little more quickly, and that those chemical changes will occur more rapidly at higher temperatures. Generally, increase of 10 degrees Celsius will double a reaction rate, which is sort of just a rule of thumb. It's not always exactly 2 times. But you can sort of understand by adding the activation energy onto a Maxwell-Boltzmann distribution why a reaction goes faster at a higher temperature. So we've got a cold sample here, and you see that most of the particles are way down here, well below the activation energy. So if these particles hit each other, nothing's going to happen. They'll just bounce off of each other and no reaction will occur. Only the particles that happen to be above the activation energy, if those ones hit, well, then you get a reaction. They have to hit each other the right way, of course. But if you warm up the sample and you push more of these particles that were going slowly here up into the higher, maybe I should choose a different color here, blue, so that looks like I'm talking about the cold one. Right, if we take some of these particles that were moving slowly and you give them more energy, that means more particles will end up being able to react. And so you have probably double the amount of particles now underneath that line that when they hit each other, they'll have that minimum energy needed and the reaction will proceed. Catalysts are a really neat way to change the reaction rate. What they do is essentially reduce the amount of energy needed for the reaction to proceed. So they do this by giving reactions a different sort of pathway that requires less energy. And so there's a smaller hill for those particles to have to get over in order for the reaction to proceed. So you'd say that this would be no catalyst, and this would be with a catalyst. So what we did there is we reduced the amount of activation energy. So this would be EACT1, and this would be EACT2. So EACT2 requires less energy for a reaction than EACT1. And again, you can see that there's a lot more particles that are going to have that minimum amount of energy. So EACT1 with the higher activation energy means only these particles, only the ones with at the high end here, would be able to have that minimum amount to get over the hump. When you reduce that amount of energy needed, well then a lot more particles, all these particles now can be added, and these particles will also react along with the other ones that were previously able to do it. So that will increase the reaction rate, and that's another neat way of speeding up reactions, or slowing it down. Of course, if you remove the catalyst, it's not going to go as quickly. So there's a couple different types that we're going to look at here. One is when the catalyst is in the same state or phase as the reactants. And so this reaction here, we've got potassium iodide, which is the usual catalyst that you add to the peroxide in order to get a reaction to go. And so once we pour the two of them together, well then the reaction proceeds because those the catalyst and the reactants are in close proximity to each other. They can mix and you get a nice speedy reaction. Another one is where you have two phases. So the catalyst might be in a different phase as the reactants. This is one you can try as well. It might be harder to try at home, but you could ask your teacher. If you take a little bit of acetone and you heat up a copper wire, the hot copper will catalyze a decomposition reaction here that gives off heat. It's exothermic, and it'll keep that copper wire glowing so you can sort of see the reaction occurring on the surface of the copper wire as those vapors interact with it. And so the copper is a solid, and the acetone reacts as a gas because it evaporates and interacts with it at the surface there. So you get two different phases, and the reaction happens at the surface. This is the same sort of thing that happens in the catalytic converter on the vehicles that we drive. There's a platinum catalyst that helps break down some of the gaseous products from engines into safer exhaust products that eventually get released. Okay, so that's it for this lesson. We'll talk to you soon.